Hello, everyone, and thank you for joining us today. Welcome to Meggert's special webinar series. Today's topic is Directional Protection Fundamentals. My name is Michael Fleischer, and I'm the Digital Marketing Analyst from Megger. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. I think we might want to cycle through a couple slides. There we go. You can submit questions at any time during the presentation by typing in that box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. Additionally, a certificate of attendance, copy of the presentation, and link to the recording of this webinar will be sent to all attendees in 2 business days. Our presenter today is Abel Gonzalez, Applications Engineer. To assist with the question and answer session, we will also have joining us Sukosh Kuber, Applications Engineer, and Guillermo Falquez, Applications Engineer. All right, let's go ahead and get started. Thank you for joining us, Abel.
All right, thanks, Mike. So today we are going to discuss directional protection, different elements, really the basics of what directionality means in faults in protection systems. And then, we are going to, at the end, going to do some testing of a directional element on a relay I have here with me. So first, let's try and do an introduction to what is meant by direction when we are talking about the system. When we're talking about the system, what is the meaning of direction to a fault? I have here a simple system with 3 sources, a couple of lines, and I have chosen the regular, circulation of currents in the system as currents here on S1. I have a relay here which has a 51 element, and the current is circulating into the line. For R2, which is the relay that I have right here, it also has a 51 element, and the current is also circulating into this line. And for this other element here, well, the conditions of the load make it so that the normal circulation of current on this relay is to the right. If we introduce a fault into the line at this point signal here, it could happen that, well, this relay is definitely, if there is a fault, is going to see an increase in the current. This relay here is also going to see an increase in the current because of the fault. But it could happen that this R3 relay now, instead of seeing current flowing into this line, it could see a circulation of a high amount of current because of the fault that we introduced in this point here, and that is going to be going in the opposite direction of the normal flow of power that this relay should see. Now, since all of these relays here, I have represented them as 51 elements, which are, you guys know, inverse over current or time over current elements. Then after some time, these relays, which they only act on the amount of current that circulates, and if that current is higher than the pickup of the relay, the relays are going to trip, and everybody is going to be, this line is going to be out of service. But in this particular condition, we are also taking out of service this source, which may mean that now the customers that are served on this line may not have enough power. The system that's left may not have enough power to serve the customers that are powered or connected to this line, and this could create a cascade of issues in the system. Now, for this reason, and we can use a great number of different examples to justify the need for a function or a relay that is capable of figuring out in which direction or where did the fault happen in the system, and to block the operation of its outputs if the direction of the in where the fault occurred does not correspond with the direction to where the relay should be looking into. For instance, this relay R3 here, it should be looking for faults in this line here, and it should only serve as backup to these relays here if that is if it is configured this way. But you should have a way or means of determining the direction or the place where the fault happened in the power system. Now, the element in the ANSI standard that deals with directionality and with the determination of directionality of fault is element number 67, which is described in the C372 from 2008 as an AC directional overcurrent relay. And what this relay does is it figures out if the fault happened in the direction into which it was programmed, and it will say, hey, yes, the fault happened in that direction, or no, the fault didn't happen in that direction. That's basically the output of a of an AC directional overcurrent relay. Of course, many different implementations exist in the market, where the 67 could be a full-fledged overcurrent element, or it could be simple supervisory element. Other element numbers that deal with directionality, and you will find in conversations or discussions, or even in manufacturers' specifications and manufacturers and user manuals of relays, etc., that deal with directionality are element number 32 and 21. The 32, directional power, is different from the 67 in that it is not looking for the directionality of the fault, but it's mostly looking for whether the flow of power in the system is happening in one direction or the other. And it also has thresholds that you can configure to know whether the power that is going in one direction or the other is greater than a particular value that you want to prevent the flow of. And element 21, which is distance element. Well, distance elements are inherently directional depending on the implementation. They could even be implemented with using a 67 element as a supervisory element, or they could be implemented without the use, let's say, specifically of a 21 element, but inherent values that have to do with the distance protection. And reversely, you can use distance protection elements to provide directional supervision or directional decisions in the system as well. Now, how do directional elements work, and how do they know if there was a fault in this direction or the other in the system? Let's consider this simple system where what I have is a source, a line, and a measurement element here. It could be a relay, or it could be a power quality meter. It could be basically anything that can measure voltages and currents in the system. And we know that under normal conditions, the system will be seeing here we will see the voltage is this green sinusoid that I have here, and I have represented the voltage vector in this chart here on the right, the voltage vector, you can only see the tip of the voltage vector, but it's actually larger than the power vector that you see below. The red one corresponds to this power vector, which is the product of these two waveforms, and this blue waveform corresponds to the current that is circulating through the system during normal operating conditions. Notice that here we have a lagging condition of the load. In reality, remember that the load could very well be in any part of this coordinate plane. It could be in any of the quadrants of the coordinate plane if the load is mainly inductive and if the load is drawing current in the forward direction, let's say, of this measurement element that we have here. Then we have this condition where the current vector could be in any place in this quadrant down here. This is known as the load, the current lagging the voltage, and we have a positive power factor in this case. Now, if we have a fault in the system, one thing that happens is that now when we introduce a fault, the current that circulates is mostly connected to the fault, given that when we have a fault in the system, it is often the case that the fault current is much greater than the load current. Under these conditions, we see that the angle of the current goes all the way very close to minus 90 degrees, and the reason for that is that the current that circulates is now equal to the voltage divided by the impedance of the line, and the impedance of the line is mostly inductive, and therefore the current that now circulates in the system has a highly inductive characteristic. And that is something that is first very important because it allows us to know that there is a fault in the system. The jump in angle between the load angle and the fault angle allows us to know that it is a fault in the system. And secondly, it allows us to kind of start figuring it out that if the fault happens and the fault happened in the right direction, let's say so in the forward direction from the relay, then we are going to have a phase relationship between voltage and current that is going to put the current somewhere in this quadrant in relation with the voltage. If the fault happens behind the relay, and here we are considering and we are showing the waveform as seen by R3, this relay that we have here, where if you guys remember from the first few slides, do you remember that for this relay there, the current was inverted from the normal flow, because now that we have the fault here, this relay was supposed to be looking in this direction. So now the current flow is inverted, and because of the polarity of the CTs and PTs of the relay, now the current, you can see it here, is almost at 180 degrees from the voltage. The voltage, although I am not showing it here, the voltage is basically has the same polarity or close to the same polarity as before, but the current was inverted, and we can see that here also in the phasor diagram that I'm showing on the right, where we see the voltage here. It remains where it was before. It's going to change in magnitude, of course, but the current is going to increase in magnitude, and it's also going to jump, but it's going to jump to the third quadrant of this um, graph or impedance graph or voltage and current graph that I have right here. Notice that now this current is at almost 180 degrees from where it was before. Now, this tells us that we can use the phase relationships between voltages and currents to determine directionality in the system. Now, that is never as simple. This just tells me the things that I can, let's say, use, the parameters that I can use, but the implementations of such directionality determinations or directional functions depend, of course, on the types of faults that I have in the system. For example, here I have, and always remember that the measurement point that I have is always here in these squares, and for the purposes of these few slides, I have represented in red only the phases where there is a fault. So in this case, we have a three-phase fault, and the current that is circulating, let's say the phase A current is going to be equal to the voltage here divided by the impedance to the point of the fault. So that means that we have, for this case, we have a condition where we have the current. We represent the current here, lagging the voltage to an angle that in this case will correspond with the angle of the line. Since the line is mostly inductive, then the angle is going to be skewed and close to the this axis here, because it's going to be very inductive. And now we see that the current is, for no matter what type of fault we have in this line, as long as the line is inductive, the current is always going to lie within this quadrant with respect to the voltage of the faulted line. In this case, all three lines are faulted, so we can do the same for all three phases. What happens when we have a fault to ground? Well, when we have a fault to ground, we have a similar condition. In this case, we simply see that instead of the impedance of the line, or just the impedance of the line, we have to consider the impedance of the neutral. But again, we are going to see that the current is going to lag the voltage, and it's going to lie in this within 90 degrees of the given that the impedance of the line and the impedance of the neutral are both mostly inductive. Now, when it comes to the face-to-face fault, we have a somewhat different case, because in the case of a face-to-face fault, now the current is equal to the face-to-face voltage, this one here, divided by twice the impedance of the line. But the same thing applies, that the current is going to be within 90 degrees, although this time it's not going to be within 90 degrees of the phase voltage, but within 90 degrees of the face-to-face voltage. Of course, the difference here is that instead of having one line impedance, we have twice the line impedance, and therefore even though the calculations, let's say, are a little bit different, the phase relationships remain, and we can do the same for other phases. For example, we can do the same for a fault between phases A and C. Now, when we put it all together, we can see that for a phase A to ground fault, the current will remain within 90 degrees of the phase A voltage. For an A to B or A to C fault, the currents are going to remain within 90 degrees, but of the line-to-line voltage in this case. What we can do is we can put these three characteristics together, and we can say that as long as the current remains in this area here, then we can declare a forward trip for this relay. And we can do the reverse. We can say that if the current is not within this with this area, then we have a reverse, and we shouldn't trip or enable the trip of the function that we are controlling with the directional element. And based on this concept, the directional relays, the directional element is designed to define, let's say, an area in the complex plane, which can be represented either as an impedance plane, or it could be represented as a polar graph of voltages and currents, which is what I have right here. And in any case, you will always see that the 67 element is represented with a forward and a reverse zone. And I like to put forward and reverse instead of trip, no trip, because we could have we could be using the 67 element to enable trips in the reverse direction rather than forward. That's why I don't like to say trip, no trip, even though you will see that in some representations, and that's fine too, as long as you know what you're doing. But what I'm trying to tell you is that since the 67 tells you whether the fault is in that direction or not, then it also tells you whether it is in the reverse direction or not. So you can use it for forward looking protection elements, as well as for reverse looking protection elements. Now, every directional element out there will have a polarizing magnitude, which in this case I'm representing here as V-pole. Most of the polarizing magnitudes that are used in directional elements are voltages, and they the angle between the origin or the reference point and this V-pole is going to be represented most of the times as MTA, or maximum torque angle. Then we will have the fault current, and the relationship between the fault current and the polarizing angle, and the polarizing magnitude, will tell us whether the fault happened in the forward or in the reverse direction. See here, I have the fault current, and I have the angle to the fault. I have this polarizing magnitude. I have the MTA. Typically, you will see this line or the border or the division between forward and reverse, which is drawn at plus minus 90 degrees of the MTA. And of course, we will see later that that is something that can be changed. You can use things called blinders to change the area of forward and reverse. We'll talk about that later, but the most common the most common representation will be a split in half of the polar plane, where on one side you will have the forward decision, and on the other side you will have the reverse decision, and it's typically within plus minus 90 degrees of the MTA. In particular, what we are interested most of all is not only of the torque angle or the fault angle, but the actual difference between what's called the maximum torque angle and the fault angle, because this angle here is the one that we use to decide whether the fault happened in one direction or the other. In particular, we use the cosine of that angle, and if, for example, the fault happened at exactly the MTA, then we would have that I've called here torque angle is 0. The cosine of the torque angle equals 1. And of course, in this condition, we need to operate. In this other example, here, I have placed the fault current at 90 degrees square with the polarizing voltage. What that means is that the difference between them is, well, 90, and the cosine is 0. And I could have also a condition, for instance, of course, we could have position the current in anywhere in the plane. I'm just using the extreme cases. But we could have the fault current at 180 degrees, in which case the cosine of the angle difference between the polarizing and the fault magnitudes is -1. And most relays, they will define, and it's not always this equation, but it is this sort of equation, where you would have something called torque, a name that comes from the electromechanical era, when you actually needed torque to move something or to keep something in place. Let's say a contact that you wanted to keep closed, or a contact that you wanted to prevent from opening. In this case, for microprocessor relays, it's simply a magnitude, a mathematical trick, I should say, that is used to determine whether we need to enable the directionality or not. And typically, you will enable the directional if the torque is greater than or equal to 0. What that means is that it will be enabled in this area here, and it will be disabled anywhere where the torque is lower than 0 or negative. And remember that the sign of this is only given by the cosine of the angle between the polarizing and magnitude and the fault magnitude. There are different ways of seeing this. I just used a few that I found in the literature. There's always way more. You will find different relays having different characteristics. You will find different relays within the same manufacturer even having different characteristics. It depends on the type of polarizing magnitude that they use. In some cases, they represent them as impedances. In other cases, they represent them in polar. So it's important that we get familiar with the user manual of the relay that we are using to figure out what those different terms mean in that particular relay. Now, polarization methods. Well, the polarizing signal is very important for the operation of the 67 element. The different choices that we have, and that there are more than this, but I have here, let's say, a subset of the choices that you have. You have self-polarization, you have the voltage of the non-faulted phases, is also known as cross-polarization, of memory polarization, positive sequence voltage, and negative sequence on zero sequence voltage polarization, and current polarization. When it comes to self-polarized elements, what they do is they use the voltage of the faulted phase to provide the reference for the decision. I am only including this here as a reference so that you guys know why this is not used in the field, and why do you not, it's rare to find elements that are being polarized with the voltage of the faulted phase. But I believe it's interesting to talk a little bit about it, so because that helps us understand the other methods that we have later. Let's say if when you have a phase to ground fault, the voltage at the measurement point here at the relay is going to depend on the voltage at the source, which is behind the relay, and the amount of current that circulates, which for a fault, it's typically a high amount of current, and the impedance of the source to the point of the relay, or the impedance between the source and the relay. For weak sources, we have that the voltage here at this point is considerably reduced with respect to the voltage on the other phases, and even with respect to the voltage before the fault. We have condition such as this, where the magnitude of the voltage present in the faulted phase can be too low, and it could be so low that we don't have enough magnitude of the voltage to make a decision about the directionality of the function. Fortunately for us, we have the help of the other two phases, because yes, the voltage in this phase is low, but since we were talking about a single phase fault, the other two phases were not affected by the fault, and therefore we can use the voltage of either of those phases, or even better, we can use the voltage of the line voltage between those two phases. That line voltage is going to be in quadrature with the faulted phase voltage, and quadrature just means that it is at 90 degrees from the faulted phase voltage. And then we can use the same concept. We can create a polarizing magnitude from this VBC. This polarizing magnitude is going to be at the MTA from VA, and then we can decide on the area where the operation should happen and should not happen. So here what we do is, typically this quadrature voltage is found and a correction of this voltage is done so that we put this magnitude at the MTA, and then we create this line, remember, at plus minus the 90 degrees from the MTA, and then we apply whatever equation we have to decide. But in this case, we would be looking at the cosine between these two vectors that we have right here. So this graph that I have here is just the same graph that I had before, but with a little bit more of detail. And I'm showing here CVBC. Now, in relay diagrams, you are not going to see this explained like this, where, oh, this is the polarizing. Typically, they go straight to the concept where they show you, okay, this is VBC, and sometimes you don't even see the VAN or anything, and then they just move to where the polarizing voltage should be at an angle that sometimes is called as a compensating angle, or the relay angle, or the relay characteristic angle, or the ECA, or something like that. And that puts the polarizing voltage at the MTA, and then, and only then, is the fault angle compared with the to make the directionality the decision. For face-to-face faults, it's similar, but then instead of using the VAB, we can use either of the faulted phases voltages, or we can use the VAB voltage, or we could use the VCN voltage, which is one voltage that was not affected by the fault. It is one of the I should say more complicated, and there is a lot of variations on how to do or the polarization methods that are used for face-to-face faults. In the case of a three-phase fault, it is important to notice that we have the positive sequence impedance of the line to the point of fault are the impedances that are used to determine the fault current. So we can use, for three-phase fault, we can use the positive sequence polarization. Now, the thing with using sequence components is that you have to have those components in the system during the fault in order to be able to use them for polarization. If you have a three-phase fault, you will not have zero sequence components, and you will not have any negative sequence components. Those values are going to be very low. And if you have a closing fault, you will probably have very low voltages on all of the phases. So you can either use the positive sequence components if they are high enough, or you can use something called memory polarization, in which the relays, typically if we are talking about microprocessor relays, what they do for memory polarization is they keep a memory of the last few cycles. Depending on the relay implementation, it can be more or less, but it's only a few cycles before the fault inception, assuming that during those cycles before the fault inception, the voltages were healthy enough and that the voltages are not going to change too much. The voltage angles are not going to change too much, so you can use them to determine the direction to the fault. Negative sequence elements, on the other hand, they're very popular, and they are used mostly for face-to-face faults, because with face-to-face faults, there is a presence of negative sequence components, which is high in that case, and it is also in a value that is not affected by the load, assuming, as it happens most of the times, that the load that we are serving is balanced enough. There is little negative sequence components in that load, and the forward fault is declared for this case. I mean, the directionality decision is made if the negative sequence current leads the negative sequence voltage by an angle that's 180 minus MTA. We can see that in this diagram here, where we have the healthy or balanced system. Then we have a fault, phase A to ground, and here we have the representation of the positive sequence, negative and zero sequence voltage, and then we have the current. See how the current in this case is leading the voltage, and therefore we can say that in this case it's a forward fault. This is a topic that we could, I believe we should do a webinar talking only about negative sequence and even zero sequence polarization, or perhaps ground element polarization. It's a very rich topic. When it comes to zero sequence polarization, we use the zero sequence voltage, the 3V0 or 3I0. And what we do is we compare the relative position of the zero sequence voltage and the zero sequence current. Now, the zero sequence voltage can be calculated today in microprocessor relays. It's calculated from the 3 voltage inputs on the relay. It could be a 4th voltage input that takes its input directly from a zero sequence PT connected to the neutral of a transformer, or we could get this input from a broken delta, as we see here. Remember that the zero sequence component, if you guys remember the equation, is simply VA plus VB plus VC, 1/3 of that. So if we use this this connection that we have here, in which we are connecting the secondary of 3 auxiliary transformers in series, and with the proper polarity, then we have VA, VB, and VC, the VA plus VB plus VC, and then we have the sum right here, and we can connect a voltage sensor to measure directly the polarization voltage, the 3V0 polarization voltage. And for the case of the I0, we can calculate it, same thing. We can calculate the residual current from the 3 relay inputs, or from any relay inputs that we have. We can use a CT and connect that CT to a dedicated CT ground input in the relay, and there are different ways of doing that. When it comes to the current polarization, then so far we have talked about voltage polarization. And with voltage polarization, what I mean is a voltage is used as the polarizing signal, okay? And then we compare that voltage with the current that's circulating during the fault, and by using the angular relationship between that polarizing voltage and the current, the fault current, then we know whether the fault happened in one direction or the other. When we say current polarization, what we are doing is we are using two currents to determine whether there was a fault. This is also a very rich topic that we could talk at length, but in general, what we do is we use the zero sequence current, and we need to find out a polarizing signal that is connected to the occurrence of the fault, as we can see in this case, where we are using the residual current here as a polarizing for the 67, and then we are using this 3I0 coming from this relay to compare the sign of them, and if they are circulating in opposite directions, then we say that the trip happened in the reverse, and if they're circulating in the same direction, then the trip happened in the forward direction. And there are many different ways of doing that. There is a very long document created by the PSRC about ground polarizing circuits, and it goes in depth into these topics. One last thing that I want to touch on before we go into the test results is the blinders that I was telling you at the beginning. And blinders are used because the thing is, it's never so crisp in protection systems. It's very difficult to say, okay, we have this 180-degree zone of operation, and then this this 180 degrees, and then this 180 degrees of no operation. What happens in the gray area where you either have not enough sensibility, the currents that are circulating are too low, where perhaps the magnitude of fault current is close to the magnitude of the load current. So for those cases, you have to protect yourself against misoperations. You have to secure your system, and you have to perform, I should say, the proper short circuit study to determine, and not just the short circuit, but also the load flow study, and compare them to determine whether you are going to have issues with the zone of operation, and then you have to decide. And those things, fortunately, in most microprocessor relays today, can be configured. You can configure this, let's say, no operation regions, blinders. There are different names for those. The last segment I wanted to devote to testing a relay that I have here with me. I have the configuration of the relay right here. This is an F60 relay that I have with me. I have configured a time over current function, and I have configured and I have enabled the directionality in the time over current function right here. We will come back to this slide probably later on if we need to check something on the when it comes to settings. And so the one thing I wanted to show you first was this is where you would configure the settings of the directional element on the relay. And notice one thing here, ECA. That's one term that I have not touched on the presentation. And because I have in the presentation, I have talked about MTA, which is maximum torque angle. I have talked, or I have said, I think RCA, which is relay characteristic angle, etc. But ECA, it's something that's not very common. Of course, once you've done this a few times, you know to go in the user manual and look, because you cannot assume that this means what you think it means. Some would think that this is the MTA, because this is how most of these relays you are used to configuring. But in this case, notice that this is actually the correction angle that you use in order to put your polarizing voltage, which in this case, and by now you guys, I hope that are already able to identify that the polarizing voltage in this case is VBC, which is the voltage between phases B and C. See here, they calculated VBC. This is VBC right here. They have VAG, which is the voltage from phase A. I mean the voltage to ground from phase A. Notice that they have the VAG unfolded. They have it here, and then they have this VAG folded, reduced in magnitude. All right, and then they put this VBC, which is their polarizing voltage. They put it at 90 degrees from VAG. Well, that's not they put it. That's where the actual vector lies when you simply transport it here parallel to where it was before and located in the center of coordinates here. And then you see this ECA, and this ECA is what sets the VBC as your polarizing voltage, because this is what converts the VBC to the faulted fault angle, which is what they set here and at 60 degrees lagging. And this is important because yes, you can test this manually yourself once you know these things, but there are tools that you can use to configure your test automatically. And in those tools, the names that you will find may be a little bit different, but as long as you understand the concepts behind, you will be able to use them to your advantage. Now, another thing that you see in this threshold here that says polarizing voltage threshold, which is 0.7 per unit, what this is telling me is that I cannot test the directional element on this relay unless I inject a voltage that is at least 0.7 the per unit value of the relay. So you have to go to the relay, see what the secondary of the VT is set at, and you have to test with that voltage, or at least with a voltage higher than 70% of that. Otherwise, you will not get a trip. So once we know those things, well, we go and get the other thing is we have to figure out what is the VT connection. This is something that is very common to get calls with our software from those who are trying to test, and they're using one of the most popular connections in the system, which is an open delta, and they have configured our test set as a Y. The open delta is also available there. You can also configure it, but you have to pay attention to that in the relay as well as in the test set. In this case, I configure them both as Y because it's easier. If you configure them as open delta, the test set will inject voltages on two phases with a 60-degree phase shift between them, and you're supposed to know how to connect the leads, the voltage leads at the relay. The relay connection diagrams typically show that it's very easy to follow. When it comes to the testing, well, I just configure the curve, configure the pickup, the time dial, the forward direction is forward. Now notice that I have configured here my MTA as 60, and I did that because I know that the MTA is typically the angle of the faulted line to the reference voltage of that faulted line. Okay, so if ECA is 30, and looking at this diagram here, then my MTA is going to be 60 for this particular case. So other things that I configured: blinder, in this case at 90 degrees. I have no setting here for blinder, and what that tells me is that I have to configure my angle here at 90, which is plus minus 90. That's what this number here means. And once I do that, if I wanted to use a different angle, let's say my zone would look something like this, then I would need to use an angle that's different from 90, maybe 75. That means that, or let's say 70. That means that I have 15 degrees on each end, and so on. So please keep that in mind when you're doing this. These tests. Now, one thing that I kind of mentioned, but was not, I guess, very clear, and I want to go back to this, is that in the relay itself, and different relays have different philosophies, and that's just something that you have to be aware of. But most of the times, the 67 is something that you have to intentionally enable in the protection function that you're using. In this case, in particular, if you enable the directional here, if you enable the directional, but you don't use this directional, the output of the directional element in this blocking points here, the function will continue to behave as if there was no directional behavior. Okay, so you need to intentionally apply the 67 to the time over current function that you want to apply it to. Okay, so it's you have to know that those things are important. In other relays, you will see it as torque control, and you can basically use whatever signal you want for torque control. In this case here too, you can basically use whatever signal you want as block for this function. One of the things that you can use is the directional, and that's what I'm doing here. And after that, well, you are ready to test. The first thing that I like to test is the pickup of the function. Now, for this, well, I configured two outputs on the relay. I used output 6 here as the of the pickup of the time over current function, and output 5 as the operation or trip of the time over current function. I connected them 6 to 2 in my test set, and 5 to 1 in my in my test set. That's why I have these 5-1 and 6-2. And then I conducted my my phase pickup. If your directional element is not properly, there are two things here. First, you could pass a pickup test even if your directional element in the relay, if this is not blocking, even if you enable this, you could pass the pickup test, and that doesn't mean that your directionality is working. Okay, it's only until you configure the actual permissive here of the 67 that you can use the phase pickup test to verify whether you are you have the proper configuration on the relay. Now, the passing the pickup is not 100% an indication that your zones are correct and that your angles are everything is fine. So the second thing you have to do, I guess, is do the timing test. But once you do the pickup, your timing is most likely going to work. This one is a little bit, I'm going to say, more challenging to pass, because this one is going to keep the operating signal at a value higher than your pickup, and it's going to move your angles from no operation and into operation. One thing that I have seen happen, I'm going to say, to some people testing, is that they try to test this because it is a trip test. They try to test it against the trip signal, and that is fine if you are testing a 50 element. But if you're testing a 51, then, and you're trying to use your trip signal, then you will see that your trip area goes into the characteristic. And what that means is that the element is getting into the zone, it's being enabled, but then it's waiting its time to trip, whatever that time is. And depending on the relationship between that time and the step that we used here, you're gonna go deeper or less deep into the characteristic. My point is, if you're doing this test, do it versus the pickup in this particular relay, and then you can do it for all of the different phases. And for the 3-phase, you will see that the test set will test at different angles, because of course not this line that I have right here corresponds to only one of the phases. The other phases are tested, with a phase rotation, and then all the values are placed in the same line right here to make it easier for you to understand. And then there is this phase directional shot that is done by basically clicking in the characteristic in places where you want to test. You could basically test around the MTA and the opposite area, but I just had fun testing and clicking in different places here. And when you run it, what it does is it runs the point for a very short time, and if there is a trip, like you see here, you will see the trip. And if there is no trip in an area where there shouldn't be any trip, then you get this pass-fail. And in the end, well, you get your test report. I guess this is all for today. As a summary, well, the directionality, well, it's important, and it's required to provide secure, selective, and fast power system protection. Directional elements increase reliability, as we saw in the case where if you're using it, you're not leaving customers or lines or even sources out of the system that shouldn't be out of the system. There are many different polarization methods, and their use is going to depend on the type of fault that you have in the system. The 67 element is usually used for supervision of other elements, and you should configure it properly. There are terms like MTA, RCA, Z1, ANG, ECA in the field, and you cannot assume that they all mean the same thing. You should always consult the manufacturer literature. It can be a tricky process testing directional elements. You have to consider things like minimum voltage, the voltage connections. Remember, if it's Y, open delta, the type of connection that you have, the phase sequence. Sometimes you think, and I had this call a couple of days ago where someone was trying to get the sequence components, and they saw that the magnitudes that they were injecting were apparently in their mind correct. But in reality, what happened was that they had an ACB instead of an ABC. So that those are things that affect directionality very much. A different phase sequence tells you that the power is running in a different direction. And of course, last but not least, the choice of binary input signal that you're using to get your trips, etc. So take some time if you guys have some to look at our videos that we have on YouTube. We have more than 100 and something videos on different instruments. In particular for the SMRT units, we have somewhere around 40 videos that you can use to learn how to use the instrument, how to test different things. And this is our contact information. And Mike, back to you for questions.
All right, awesome. Thanks, Abel. So at this time, the presentation portion of our webinar is officially concluded, and we'll be jumping into a Q&A segment here shortly. If you have any questions, please submit them now into the Q&A box on the GoToWebinar control panel. For those of you that are leaving, when you close the webinar window, a survey should pop up on your screen. We would greatly appreciate it if you could take a couple of minutes to provide your feedback so we can continue to improve upon our future webinars. On the survey, there is a field for you to request a quote or a demo on any Mega products if you so choose. A copy of this presentation, certificate of attendance, and a link to the video recording of this webinar will be emailed to everyone in about 2 business days. You can also view video recordings of previous webinars as well as register for upcoming webinars on our website at us.mega.com/webinars and register for our next webinar on next Friday, November 19th, titled Best Practices and Techniques for Cable Fault Location and Special Applications, presented by Joseph Aguiar. All right, we're going to jump into our questions. The first one I have, I'm going to direct to our panelist, Guillermo. Guillermo, what is the difference between a 67 and a 32 element?
Thank you, Mike. First of all, can you hear
me? Yeah, I can hear you just fine.
Okay, thank you. Yeah, I just wanted to confirm. Well, a 67 is a directional overcurrent element, and it only deals with overcurrent protection. It's a type of overcurrent protection that includes directionality. So you need to, it's only looking at current, a rising current, and the direction of that rising current. 32 element, it's a reverse power element. That means that in order to have power, you need both. You need current and a voltage. You must have a voltage. The whole presentation that Abel had, he was talking about a polarizing signal and a operating signal. And both of those, the operating signal is always a current, but the polarizing signal, it could be a voltage or it could be a current. Therefore, you don't have power if you have the same, if you only have currents. For a 32 element, you're looking at both, at the direction of the voltage and of the current, and you could also set a 32 element to look at kVA, or you could set it to look at kilowatts, or you could set it to do VARs, and all those would be reverse power elements. Thank you.
Thanks, Guillermo. Our next question is going to go over to our other panelist, Sugosh. Sugosh, can current transformer saturation affect directionality?
Thanks, Mike. So yes, CT, when it saturates, we do know that the primary current is not correctly mimicked on the secondary side, and and that is what the relay reads as a current. So obviously for a directional protection, since the current can be used as an operating quantity or even polarizing quantity in some instances, it's very important for that current to be accurate. And once there is saturation, the magnitude and the phase angle of that current could cause the relay to see the direction in a way that it would cause a trip. So yeah, definitely it would affect your protection.
Thanks, Ghosh. Back over to Guillermo. For electromechanical relays, there's no memory. In that case, how does the relay work for a three-phase fault? Because all line-to-line quantities are affected.
Yeah, you're absolutely right, and that is one of the reasons why one of the first things that were implemented in microprocessor relays was the positive sequence and the negative sequence directional elements. Because obviously when you have a three-phase fault, all your polarizing signals could go down to zero to levels that are not reliable. So that is when symmetrical components and positive sequence and negative sequence, especially for three-phase faults, positive sequence directional elements would be much more accurate and reliable in that case when compared to the protections that electromechanical relays could do. Luckily, three-phase faults are not so common. So most of the systems you will see in the field will have quadrature that are using electromechanical relays are going to use a quadrature protection element since those would be reliable for unbalanced faults, which are more predominant. Thank you.
Thanks, Guillermo. Over to Sigosh. Can you explain directional supervision?
Okay. Yeah. When Abel was going through the summary, he did mention that directional protection can be used for supervision. So what it means is that, for example, you could use directional element to supervise the distance protection. Because the directional element, it adds additional security to your distance protection. An example to elaborate on that further would be, let's say we have a ground distance protection, that is there, and basically for this ground distance element, it uses your residual current as your operating quantity, right? Now, let's say if it's a forward set ground element, but it can, if there is a closing fault, which is which is in the reverse direction, and it's a ground fault, this particular element can pick up due to another phase, and because we have this residual current that is being used as the operating quantity, the element can pick up. So in this case, this is where you could use the directional element to supervise your ground distance element, just as an example.
Thanks, Coach. My next question is going to send over to Guillermo. Guillermo, how does memory polarization work?
Yeah, so memory polarization was brought by microprocessor relays, since what they're doing is they're taking an analog signal from PTs and CTs and then converting it to a digital signal. All those signals are discrete signals that are stored in memory. So in the event, let's say you have a single line to ground fault and your voltage VA goes down and it becomes unreliable, what the relay does is it looks back at a couple cycles back on its memory and looks at the voltage that was on either the quadrature voltage or the phase voltage, whatever it's using for polarization, and it uses that registry memory as the reliable source of the polarizing voltage, not the actual sample polarizing voltage or current that it's using at that moment. So that's a feature, an optional feature that the customers could enable or disable depending on their criteria or if they want to use it or not. Thank you.
Guillermo, and while I have you, I'll send this next one over to you as well. That is, what is the negative sequence physically?
So negative sequence or symmetrical components in general, it's a mathematical tool. There's no real physical interpretation. I guess with zero sequence, you could measure, you could have an open delta voltage and a zero sequence CT, but it's still measuring the residual voltage and the residual current, which happen to be the zero sequence. But all sequence components are I think of them as a transform, like as a Laplace transform. It's a mathematical tool that happened to explain more accurate different phenomena that happen in power systems. So the only representation that I could have of negative sequence is if you think of a motor, and positive sequence voltages and currents are the sequence components that make the motor spin in whichever rotation it's supposed to spin. So if the motor is supposed to spin on the counterclockwise direction, positive sequence components will make the motor spin in that direction. Negative sequence components will make the motor, will work against that. And that in the physical world will translate to noise, it will translate to heat, it will translate to losses, to power losses. So that's the only way that I could translate it into physical terms, but I will not advise anybody to think of any symmetrical component as a physical as something that exists. No, it's a mathematical representation of things that are happening that help explain different phenomena in power systems.
Guillermo? On my next question, I'm going to send over to Sagosh. Sagosh, is it possible to have multiple polarizing options for directional protection?
Well, in one way, you could have a combination of, like a dual polarization for that directional element. So let's say a particular relay has a zero sequence-based directional element. You could have multiple options, like combination of a zero sequence voltage polarized element and a zero sequence current polarized element. So this element would provide you more flexibility than having a single method of polarization. So let's say, for example, if the zero sequence voltage that the relay is reading for a fault it's too low, and the torque produced by the zero sequence voltage element, it's too low to even cross the minimum threshold, right? Then in the situation, you would rely on the zero sequence current polarized element. Okay, so vice versa works as well. So there is something called as combination of polarization you could use to protect your system using the directional protection.
Thanks, Sagosh. Back over to Guillermo. Guillermo, what are the limitations of positive sequence and/or negative sequence directional elements?
Yeah, so this ties into what Sagosh was mentioning on the previous question, and I think it was one of the questions that was asked. So when you have positive sequence components, usually, well, it's not usually, it's because you have a balance fault. If you only have positive sequence components, so a positive sequence directional element will not be the most accurate way to detect an unbalanced fault, directional fault. It's only used for balance fault. Negative sequence components, on the other hand, or negative sequence directional protection, it's used for unbalanced faults. That's single line to ground, face to ground, or face to face faults. So the ideal scenario is that you use both, the combination of both, to provide the most accurate protection in your system.
Thanks, Guillermo. Over to Abel. Even though normally MTA equals 30 to 60 degrees, if MTA is set to a very low value, such as 5 degrees, what is the impact on the relay behavior during a fault?
Well, okay. One thing that's important to, I guess, know is that MTA is related to, but is not the angle of the line. That is important because a lot of times it's confused, the MTA with the angle of the line. That said, the MTA should be set to a value high enough to allow the relay to pick up faults that are close or that are happening at an impedance that is related to the impedance of the line. And an MTA of 30, 45, 60, it's typically selected for that reason. If you make the MTA too low, you are probably going to be missing faults that are happening with the high inductive components, faults that are very close to the 90-degree angle of the line. So I would advise against that. Always, the most important thing is do a short circuit study of your system. I guess it would only make sense to me if you have some sort of capacitive compensation in lines, and you have to. But again, in that case, you have to do a proper short circuit study and configure your line. But it's not something that I can advise one way or the other without knowing the exact characteristics of the system that you are trying to protect.
Thanks, Abel. Our next question is over to Guillermo. Guillermo, what is the difference between what is the difference of MTA and ECA?
Okay, so ECA is the characteristic angle, and is used. I mainly know of GE relays that use that terminology, the ECA, and it's Abel mentioned it at the beginning of its slides. It's a compensation angle that GE uses to calculate the MTA. So one of the things that Abel mentioned in his presentation is different relay manufacturers use the same terminology, but it might not mean the same thing. So this ECA for GE relays, it's a compensation angle that they use for the polarizing voltage in order to shift your protection zone. But I would advise the customer to look into the particular relay and the characteristics of that particular relay in order to determine exactly what the ECA setting works and how it relates to the MTA.
Thanks, Guillermo. Next is over to Abel. Abel, is it possible to use IEC normal inverse for overcurrent and earth fault protection function in directional protection, or shall we select IEC definite time?
Okay, well, I guess that the answer to this is basic. It's similar to the answer I gave to the last question. Your short circuit study will allow you to properly coordinate the protections in your system. If your coordination tells you that you can use this or that curve, then you can use this or that curve. It's not crisp. I can use this for fault, and then I'm sorry, for phase faults, and I can use this other for ground fault. It's not like that. It's going to depend on, again, the particular conditions of your system. As an anecdote, the couple of days ago, I was talking to a CT manufacturer who was complaining about a customer asking them for a CT, and the only thing that the guys knew was the load that they were going to run in that place. They didn't know the short circuit level. They didn't know what they were going to connect to the secondary of the CT, how far the CT was going. So my point is, the more information you get from your system, the better you are going to have your system design. And your short circuit study should be the basis for any decision that you make. And with that, the coordination study that you do in the system, that will tell you whether you can use IEC, any of the inverse time over current, or the definite time curve for the system. Okay.
All right. Thanks, Abel. And while I have you, the next question will also go to you. That question is there an existing one-touch plan for F60 directional testing using RTMS?
Okay, that's a good question. Right now we have about 120 different one-touch modules, as the person who was asking puts it. We have an F35, which is very similar to the F60, and we should come up with the F60 soon enough. But the F35 can basically be used to test the F60, most of the F60 functions. All right.
All right then. It looks like we're running out of time for our Q&A, so unfortunately we're going to have to call it here. We apologize if we didn't get your question live today, but we will be following up with you offline. But as a reminder, a copy of this presentation, a certificate of attendance, and a link to the video recording of this webinar will be emailed to everyone in about 2 business days. I'd like to thank you all for attending. If you could, please remember to answer our survey. That survey will include a field for you to request a quote or demo if you're interested. But once again, I'd like to thank you all for attending, and I hope you all have a great week.